Cool, so this is the second half of lecture 2.2. If you remember, we were just now talking about these limits right here, and they're limits that you should probably have memorized. If you haven't already watched the first half, stop and go back to the first video. When you come back, this is a pretty short video. I'm just going to do some examples. So having seen this idea that a limit at infinity is really just a horizontal asymptote, and it could be a horizontal asymptote on the right-hand side or on the left-hand side, we're going to use these three limits to build out ways to solve more complicated limits, just like we did last week. And we're going to use limit properties. Your book has this list of limit properties. You should know them, you should read them, you should write them down. I'm not going to spend a ton of time right now reading through every one because you'll recognize them. They're actually the same limit properties that we did when we were doing limits at specific numbers. So these limit properties all hold, and that's great news because it means you can combine and rearrange limits to isolate the pieces that you want. But one word of warning, they're not quite as obvious as they might appear. In particular, you may find yourself tempted to split limits that don't actually meet the premise. I'm going to be a little mysterious and I'm not going to say what the premise is. I want you to read this and figure out what do you have to check about the pieces of your composite function before you know that you can actually split it into two pieces. Think about that and pause the video while you copy or think. And then we're going to continue with another example. So let's look at these examples. I'm actually going to work out the second example first. The basic idea is that I can't solve this limit by plugging in because it doesn't mean anything to plug in infinity on the bottom. And even if I did, there would be infinity on the top, and infinity divided by infinity is kind of weird. Who knows what that is? Certainly not a real number. So we're going to have to use limit properties. Here's my limit. Well, the first thing that I know is that I know that this fraction is the same thing as x over x plus 1 over x. That's just algebra properties, and I haven't taken the limit, so I'm going to make sure that I'm still using my limit notation. X approaches infinity, and I'm just trying something. I don't know if this is going to help. Think about our problem solving seminar. It may be that this is not helpful, but looking at what I've tried, what I know is that x divided by x is the same thing as 1, and that seems to me to be a little bit simpler than what I started with. Now, 1 over x, I recognize that. We just talked about the limit of 1 over x. I know what the limit is as x approaches infinity. So, because I know what the limit of a constant is, no matter what, and because I know what the limit of this is and it's defined to be a number, I am allowed to split this limit, which still, by the way, makes no sense because if you look at it, you can't just plug in infinity. But whatever it is, it has to equal the limit as x approaches infinity of 1 plus the limit as x approaches positive infinity of 1 over x. Well, the limit of a constant, even at infinity, is just that constant because this is the horizontal line that goes straight through the graph. Its y value never changes. And right here, the limit as x approaches infinity of 1 over x, that's 0. And that's a known limit. We proved it in the last video, and that's why I can write it right there. Well, and 1 plus 0, sure enough, is 1. I have algebraically proven this limit. If you want, you could actually go back and look at your calculator and use a table or a graph to confirm it, but this is what I would expect to see on a quiz or a test to prove the limit for me. Let's do another one. All right, this is where it gets good. The limit as x approaches infinity of sine of x over x. Observe for a moment, we're wondering what happens to this graph when we go way, way, way out to the right-hand side. I have no idea what this graph looks like, so I can't answer that question. You may or may not have a calculator. Don't pull it out. Pretend like this is on a non-calculator free response section of the test. Let's see what we can do. Well, my initial instinct sometimes is to do something like this. I know that I can rewrite this using a product rule, so maybe I'll split it into sine of x over 1 times 1 over x. And I know that I can do that because that's just an algebraic step that we're allowed to take. If this is going to help me, the next step is probably to split the limit into two pieces. But remember that premise, the one that I warned you about. You can only split this limit into two pieces if both of them are defined. We know that the limit as x approaches infinity of 1 over x is 0. That's a known limit. But we also know that the limit as x approaches infinity of sine of x is undefined. That's not a known limit. So actually, you're not allowed to write limit as x approaches infinity of sine times limit as x approaches infinity of 1 of x. This actually isn't going to work. And if you think about our problem solving activity that we did, sometimes that's what happens. And actually, I'm going to now nominate, since there's nothing else I can do here, I'm going to say that was not helpful, and we're going to try something different. So back to the drawing board. Here's sine of x over x. Well, not only do the limit properties hold from our normal limits, but the squeeze theorem actually also works for limits at infinity. So observe for a moment, and this is kind of some scratch work, so I'm just going to draw a little thinking bubble, and this is not part of my work that I'm writing up. I'm just going to observe. I know that sine of x, the function sine of x, its output, is always in between positive 1 and negative 1. These values, that sine function that oscillates up and down, the answer here never gets greater than 1 and never gets smaller than negative 1. Well, that means that if I take sine of x and I divide it by a positive number, and positive is important here, the answer is always going to be smaller than 1 divided by that positive number, and larger than negative 1 divided by that positive number. Now, why is it fair for us to assume that x is positive? Well, we're really interested in x as a large positive number, so that's a fair assumption to make. If x was negative, these symbols would have to flip. That's just an inequality rule. Don't stress about it now if you're not sure what I was saying. The important part is that you're with me when I say that sine of x over x has to be greater than negative 1 over x for the same x value. We don't know what it is, but for any x value, this is going to be greater than this, and this is going to be less than this. And these are the exact conditions for the squeeze theorem, because the limit as x approaches infinity of negative 1 over x, which is just the reciprocal function reflected over the x-axis, is 0. And that also equals the limit as x approaches positive infinity of 1 over x. And since the two outside functions have limits at positive infinity, and their limits equal each other, this middle function is squeezed in between, and this is considered proof that the limit as x approaches infinity, I know I'm at the bottom of the screen here, of sine x over x also equals 0. And what you would usually write to prove your point is you would write this work, and then this line, and then you would say by the squeeze theorem. Done. Beautiful. Awesome. Now the other beautiful thing is, now that I've proven that this limit equals 0, you can take that as a known limit, and you can use that, for example, in the one that you're going to do. Pause the video, work out the one for you. When you're done, I'll show you how I worked it out. Alright, this is a great one. I'm not sure how far you got, but here's what I would do. The first thing that I see is that plus, and I know that one thing I could do, although I don't know if it's going to help me, is I could rewrite this inside term, splitting out two fractions. So I've got the limit as x approaches infinity of 5x over x plus sine of x over x. And again, I'm just playing around with the algebra. Now, if I were doing the problem solving activity, I would then reflect, does this look like it helps me or not? On the one hand, maybe it looks a little more complicated, but the other hand is I start to recognize this, And that looks familiar to me. So usually it's a good sign when you start to see things that are somehow familiar. Now, before I can split this into two limits, I need to confirm that both of these limits exist. Right now, I'm still unsure about this because plugging in infinity and dividing it by itself is nonsense. You can't do that. But there's a little bit of algebra I can still do because x divided by x is really just 1. So actually, instead of 5x over x, I can continue to algebraically manipulate this, and in fact, 5x over x is really just 5. And now I see that I can actually split my limits. I can do that because this is going to be a limit of a constant, which exists and is a number. And this is going to be 0, as we just saw, because we just proved this one together. So since I've checked my premise, I am allowed to split this limit into the limit as x approaches infinity of 5, plus the limit as x approaches infinity of sine x over x. And this limit equals the number 5, and this limit equals the number 0. And so our answer is 5. Hooray! I'll see you in class.